In this video, we're going to talk about Kubernetes itself. First off, what is it? At the most basic level, Kubernetes is a system that runs Docker containers for you. It has a powerful labeling system that allows you to manage your containers in lots of interesting ways, as well as the ability to run containers on multiple machines. These capabilities scale up really big. In fact, Google is running their entire Docker-based platform on Kubernetes. It's called Google Container Engine. Here's what a Kubernetes cluster looks like at a really high level. It's made up of several machines. One of them is designated to be the master. This is the host for the Kubernetes API, which is how you interact with the cluster as a developer and tell it what to do. The rest of the machines are minions. These are the machines that actually run the Docker containers. They talk to the master and do what it tells them to do. The basic building blocks of any Kubernetes system are pods. A pod is the atomic unit of runtime in Kubernetes. It's a collection of Docker containers that you want to be run. For our purposes, this will usually be just one container, but you can have many more. The Kubernetes networking model makes it seem like each pod has its own IP address, so all the containers in a pod feel like they're running on the same machine. Usually, you won't be working on the level of pods, though, because Kubernetes has the concept of a replication controller. A replication controller, or RC, manages the lifetime of pods. You give it a target number, and if there aren't enough of the right kind of pod, it'll start more. If there are too many, it'll stop some. The way an RC knows which pods to count is through the use of a labeling system. This is a pretty powerful system that enables all kinds of interesting things. Every pod has a set of labels, and every RC manages a set of pods that match those labels. This is easier to understand with an example. Let's say I've got two pods. Both of them have a name label with the value front end, and both of them have a version label with the value 123. Both of these pods are managed by an RC, which is configured to match both of the labels. Name equals front end, and version equals 123. Now we're going to add a near copy of the first RC, but instead of running this pod, it's going to run a newer version of it, version 124. We're going to give it an initial replica count of 1, and I'll tell you why in just a minute. Now this new replication controller will notice that there's no matching pods in the system, so it'll start one. Now its count is satisfied, and it just lets the system run. Now we have 3 pods running, so how do we route traffic to them? In Kubernetes, this is done with something called a service. A service is like a load balanced DNS entry. It distributes traffic to pods using labels. Let's define a service called frontend and give it the matching criteria of name equals frontend. Now you can see that it matches all 3 of these pods. All of them have the name frontend, even though they're of different versions. If any container running in this cluster does a DNS lookup for the name frontend, it'll get the IP address of the service, and when it tries to connect to that, the traffic will be passed to one of these 3 pods. Now let's change a couple of numbers. First, we'll ratchet the first RC's count down to 1, and since it has too many pods now, it will stop 1. Then we'll turn the second RC up to 2, and it will notice that it doesn't have enough, and it'll start another one. Finally, we'll turn the first RC down to 0, and it will stop its final pod. And then we'll go ahead and delete it because it's not doing anything for us right now. Now what we've just done is replace the old versions of this front-end pod with a new version, one by one. And there was no downtime because the service was distributing traffic smoothly among all of the pods and all of the versions. In Kubernetes, this is called rolling update, and it's such a common scenario that there's a simple command to wrap this whole process up. Zooming out a little bit, here's our Kubernetes cluster. There's a master and some number of minions, it doesn't matter how many. On the minions, they're running a bunch of pods. We don't really care where they're running, we just know that they're running. The pods' lifetimes are controlled by a bunch of replication controllers, and a set of services is distributing traffic to them, both from inside and outside the cluster. Let's go back to the 2 big questions we ask ourselves when we're considering a Docker-based system. How does a container get traffic from the outside world, and how does my container find another container? In Kubernetes, the answer to both of these questions is services. Inside the cluster, there's a DNS system that's populated by services. So every service gets a DNS entry the same as its name. When a pod, any pod, asks for service B, it gets the IP address of the service object, which will then pass the request off to one of the pods it's distributing load to. In order to route traffic from the outside, services can optionally generate an ingress point. When a service is configured this way, 2 things happen. The first is that a specific port is allocated on each minion for every port in the service's definition. So if my service specifies that it's routing traffic for port 8000, that might be port 37612 on every minion. but it's the same port number on every minion in the cluster. The second thing that happens is that depending on where your machines are running, something is created that balances traffic to all the minions on that port. In the Amazon cloud, which is what we'll be using in these videos, this is an ELB, an elastic load balancer. So the ELB has a name that works anywhere in the world, and when you type that into your browser, the traffic goes to one of the minions on a specific port, and that traffic goes to the service, which then distributes it to the pods. Okay, before we get any more concrete, let's summarize and tie this video up. Kubernetes is a really powerful system for running Docker containers. The building blocks it provides are flexible, capable, and while there's kind of a lot to learn, there's some new terminology, this knowledge will pay off in the future. It's been said that Kubernetes lets you think of your entire cluster as a single computer, and the rest of this video series is dedicated to showing you how. In the next video, we'll talk about the Amazon cloud and how it can help us run these kinds of applications.